let's talk about some organic bases. And those are characterized by the presence of an atom with a lone pair of electrons that can bond to a proton. Let's take a look at methylamine here. A methyl, meaning there's a methyl group on the end, carbon group. An amine, it's an NH2. Pretty easy to remember that. Well, methylamine is going to accept a proton pretty much all the time. It has no problem with that. Nitrogen's a little bit electronegative, pretty electronegative, and that lone pair of electrons is lonely. Get it? And now you're going to get N like this. And you're going to get trimethylamine. That's the conjugate acid of methylamine. And here's a question for you. How strong do you think that is? How strong is it? As reactive as this base is, you can bet that the conjugate acid is going to be pretty stable. But you know something? If you give oxygen a strong enough acid, it'll do this too. It doesn't want to, necessarily. If I just shove a proton in oxygen's face like this, what you're going to end up with here, this OH2, and this lone pair ends up giving oxygen a +1 formal charge. And oxygen does not like that. Not a fan. It's definitely not a fan. So you're going to have to encourage it with some strong acid to do that. It's not just going to want to do it on its own. And you might remember in the last video that this acted as an organic acid of its own. It's certainly willing to do that, but it's also willing to act as an organic base, which means it's amphoteric. That means it goes both ways as an acid-base combo like that. Acetone, the same way, it was an acid in the last video, but now, instead of forming this negative ion here that can delocalize its electron and do so, we're asking oxygen to take on a hydrogen proton, a proton, i.e. like a hydrogen ion, a positive charge, and form a bond with it that way. So you would end up with something like an OH here, like that. But again, you're going to see this +1 formal charge if it was just doing that. So it's not going to want to do that necessarily so easily unless it's encouraged by a stronger acid than it is. Let's take what we've learned and build something cool. I'm going to put an amine on some carbons like this. Okay, what you're looking at here is alanine. It's an uncharged version of it. This is an amino acid. That's a building block for life. And it exists as a Zwitter ion. What that means is that it charges itself. I'm going to show you how. I'm going to put a third hydrogen here, and this is going to have a plus charge in front of it. And that's still going to look the same. We're going to come over here, and that's going to look the same, and we're going to come over here. And this oxygen has lost its hydrogen because this amino acid, imagine if there's 2 of them or 3 of them or 1 billion of them like in real life. Let's put them together. What are you going to get? This carboxylic acid group is going to react with this amine group right here. And alanine is going to steal its own hydrogen to bond here and form this NH3+. And that means that this oxygen is going to end up negatively charged. So what you have here is this kind of back and forth behavior. It's called a Zwitter ion, where you end up with a polar molecule that didn't start that way, only because it interacts with itself. One side of this molecule is so willing to be an acid, and the other side is willing to be a base. All it has to do is get in touch with its twin, and you're good to go. So we're going to talk a lot about organic bases here, but I wanted you to kind of see this and get just a little bit of an introduction before we go forward. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.